Okay, so we've established that identification is possible if we adjust for confounding, such that the conditional independence assumption holds. But how do we actually take this forward for estimation? So that's what we're going to look at now. We're now going to look at methods for causal inference that actually allow us to estimate causal effects. I'm going to start by looking at outcome regression, which is going to be familiar because we've spent a substantial part of this course covering regression models. So this is the average treatment effect given the conditional independence assumption, and we've said it can be identified in this form here. So let's see here, D is a continuous treatment. This expression here would give us it would identify the average treatment effect that arises from treating units at level D relative to D0, where D0 is some reference level. And what should become immediately apparent for you looking at this lecture is this is just the difference of two conditional expectations, and we spent most of this course focusing on how we can model conditional expectations, and that is using regression. So we can use regression to model the condition expectations above and then apply averaging over the covariates x over confounders x to estimate this equation. So here's a simple example, and so we don't have to spend a lot of time actually on outcome regression because it's so familiar. All I want to point out is how we get causal estimates from regression. So consider a regression model with two continuous variables, a treatment variable and confounding covariates. It's in conditional expectation form here, which we're going to use to approximate an average treatment effect. If x satisfies the CEA, then for some fixed d equals value d or d equals value d0, the relevant average potential outcomes above could be estimated by estimating this regression model, retrieving the estimated parameters, taking the fitted values, plug in d, plug in d0, and subtract the two. And it's as simple as that. And by the Gauss-Markov theorem, the estimates that we get for these models are best linear unbiased estimators and are consistent via application of a law of large numbers. So it's as simple as that. That's how we would estimate that quantity there. This is the identification equation. That's how we go about estimating it using regression. Now that's a simple linear model, but actually the potential outcomes framework is non-parametric. When I say non-parametric, I don't mean in terms of its functional form, I mean in terms of the parameters that govern the form. So potential outcomes framework, which really just expresses things in terms of probabilities or expectations, it doesn't tell us, it doesn't dictate what parametric form we must use, and therefore it applies whichever form we use to model the conditional expectation function. So for non-Gaussian data, the function could be estimated via a generalized linear model, a generalized linear mixed model, a GAM, a semi-parametric model, or all of the other approaches that we've looked at in the course. And it's exactly the same principle. So if we have an outcome regression model, which we'll denote by this expression here, this is an outcome regression we're using to model a CEF, a conditional expectation function. It has a known link function and some linear predictor, doesn't matter the form, semi-parametric, polynomial, doesn't matter. As long as that model is correctly specified, then the average treatment effect can be consistently estimated in the binary case by averaging over the fitted values of that model evaluated at 1 minus 0, or in the case of multivalued and continuous treatments, averaging over the fitted values of that model, plugging in a fixed value of the treatment small d, or 0. So simply taking the mean of the predicted values of the outcome regression model with d held fixed at some value d gives a consistent estimate of the average potential outcome. So really, the only key insight that we need to learn about regression from a causal inference point of view is that we need to adjust for confounding in the model. If we have sufficient confounding variables to satisfy the conditional independence assumption, then regression estimates have a causal interpretation. That's how we do it. And remember, that's confounding covariates. The regression doesn't need to include every determinant of y. That's not the point. It only has to include the treatment that we're interested in, and enough representation by covariates to adjust for confounding. And remember, a confounder is a variable that influences both outcome and assignment to the treatment. All we need to do is adjust for that. So direct covariate adjustment then can be achieved by including a sufficient set in the model, as I've just said, but the data generating process is in general not known, and in fact there's no way to objectively test whether the conditional independence assumption has been satisfied or not, and that's a real challenge in causal inference. Theory provides a basis upon which sources of confounding can be hypothesized, and this requires us to think carefully about the causal structures that we believe are embedded in the data, which is ultimately what we want to model. If the assumed data generating process indicates that there are confounders that we can't observe, then we cannot achieve identification and an outcome regression model will fail, and we shouldn't attempt to use it in order to achieve causal inference. In some settings, when we've got longitudinal data, which we've talked about before, we can use dummy variables, we can use lagged variables or proxies to provide a reasonable enough approximation to omitted confounders or unobserved confounders to satisfy the conditional independence assumption. But the key point is to determine whether we believe that the variables that we have, the X variables, are sufficient to satisfy the CIA. If they are, then we've got causal estimates, causal interpretation of our regression estimates. If they're not, then we do not have a causal interpretation of our regression model.